In this chapter, we begin by introducing Schrödinger's wave equation and showing how, for a time-independent potential, the full wave function can be separated into a spatial part and a temporal part. We then obtained the time-independent Schrödinger equation, which is the equation we will most often solve in practical quantum problems. Now, an important question naturally arises. Even if we can solve Schrödinger's wave equation mathematically, what exactly does the solution mean physically? What is the physical interpretation of the wave function? That is the next major topic in this chapter. So at this point, we are entering the section on the physical meaning of the wave function. Now we come to one of the most fundamental interpretive questions in quantum mechanics. What is the relationship between the wave function and the electron? As shown earlier, the solutions to Schrödinger's equation with a time-independent potential are inherently complex valued, as shown in this expression. So the question becomes, how can psi of r and t be related to real physical measurements on a system? The answer was proposed by Max Born in 1926, and this interpretation is now one of the cornerstones of quantum mechanics. Born postulated that the square of the absolute magnitude of the wave function times the volume element d cubed r gives the absolute probability of finding the particle in the volume element d cubed r at position r and at a given time t. This statement is crucially important. It tells us that quantum mechanics doesn't generally predict the exact position of a particle with certainty. Instead, it predicts the probability of finding the particle in different regions of space. The square of the absolute magnitude of a wave function, which equals the wave function times its complex conjugate, is therefore called the probability density function. In one dimension, it is the probability per unit length. In two dimensions, it is the probability per unit area. And in three dimensions, it is the probability per unit volume. Now, if the wave function is expressed as the product of a purely spatial function and a time-dependent phase factor, as shown here, then its complex conjugate is simply given by this expression. Also, in Cartesian coordinates, the volume element, or the differential volume, is simply given by dx, dy, dz. So when we write the expression shown here, the square magnitude of the wave function times the differential volume, we are referring to the probability of finding the particle inside a tiny rectangular volume element in Cartesian coordinates. So this is a major conceptual departure from classical mechanics. In classical mechanics, if you know the initial conditions precisely and the forces are known, then in principle the future position of the particle can be predicted exactly. But in quantum mechanics, even with complex knowledge of the wave function, what we obtain directly is not an exact position but a probability distribution. This is why the wave function is so central. It may not itself be directly observable, but once we know it, we can calculate the probabilities of different measurement outcomes. Let's now examine what happens to the probability density for a stationary state. Recall that for a time-independent potential, the wave function can be decomposed into separable solutions of the form. So the probability density, the absolute square of the wave function, is simply given by this expression, as the exponential factors cancel each other out. As observed, the probability density is position dependent only, it is a real number and it must be non-negative. This is a very important result. It tells us that for a separable solution of the time-dependent Schrödinger equation with a time-independent potential, the probability density doesn't depend on time. So in a quantum system with a time-independent potential, a state whose wave function has the form shown here is called a stationary state. We see that for a stationary state, although the wave function itself does depend on time through the phase factor e to the minus I capital E times t divided by the reduced Planck constant, the measurable probability density doesn't. That's why the state is called stationary. This reinforces the idea that psi itself, which is called probability amplitude, is not the directly physical quantity, but its squared magnitude is. The concept of probability density is illustrated in the figure shown here. The curve represents the probability density distribution along the x-axis. So you would be quite likely to find the particle in the vicinity of point A, where the probability density there is the largest, and relatively unlikely to find it near point B. The probability of finding a particle in the interval between A and B is the shaded area under the graph, and can be obtained using the expression as shown. So if the probability density distribution is stationary, then the curve you see here doesn't change with time. It stays as it is forever. Please note that since the probability function is independent of time, we will, in general, only be concerned with the time-independent wave function. Let me emphasize the term stationary again. It doesn't mean that the particle is sitting motionless at a single point in space. Instead, it means that the probability distribution is fixed in time. The wave function still has a time-dependent phase, but that phase doesn't show up in the absolute square of the wave function. So if you were to repeat an experiment many times on identically prepared systems in the same stationary state, the statistical distribution of measured positions would remain unchanged over time. So please keep in mind that for a stationary state of definite energy, the corresponding probability density doesn't change with time. So here we restate the form of a stationary state having a definite real energy capital E. Mathematically, a stationary state takes the form of a spatial function multiplied by a time-dependent phase factor, e to the minus I capital E times t divided by the reduced Planck constant, where psi of r is the solution to the time-independent Schrödinger equation. Conceptually, the interpretation of that state is statistical. The wave function doesn't tell us a particle's exact position in the classical sense, but the square of its absolute magnitude tells us the probabilities for different possible measurement outcomes. Before we end this section, we need to draw out the deeper conceptual consequence of the Born interpretation. The statistical interpretation introduces a kind of indeterminacy into quantum mechanics. That is, even if the wave function is known completely, if we want to know the exact position of a particle such as an electron, the theory doesn't tell us the exact outcome of an individual position measurement in advance. Instead, it tells us the probability distribution of possible outcomes. So all quantum mechanics has to offer is statistical information about the possible results. This is one of the most profound differences between classical mechanics and quantum mechanics. As we mentioned earlier, in classical mechanics, the position of a particle or an object can, in principle, be determined precisely. If we know the initial position, the initial momentum, and the forces acting on the particle, then the equations of motion determine the trajectory exactly. However, in quantum mechanics, by contrast, the position of a particle is described in terms of probability. What the theory predicts is not a definite trajectory, but a probability density describing where the particle may be found. This doesn't mean quantum mechanics is vague or incomplete in an ordinary sense. On the contrary, the theory gives extremely precise predictions for probability distributions and observable averages. But the form of that precision is statistical rather than deterministic in the classical sense.